Hello friends, so for this video we're going to be talking about the molecular interpretation of entropy, and we'll be doing one practice problem with it. So in this case, entropy measures how many microstates are going to be associated with a singular macrostate. So what this is referencing, for example, a liquid. The liquid itself, let's say water, is going to be a macrostate, right? The macrostate of this compound, H2O, is a liquid. The microstate, however, there are individual molecules inside of this water that are actively acting as to how this water is going to behave, whether it's going to be a gas or more solid-like. So in order to calculate this, there is a way. There's this equation right here, which is entropy is equal to K natural log of W. And the K right here is going to signify the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. And W signifies the number of microstates. So as you can see, W is going to be a massive number. It's going to be huge because in this singular compound of water, we have a bunch of molecules. And all of these are behaving in different ways. So what are those ways that they can behave? Well, there are three main types. There's translational, which is linear movement. You can think of this as just a molecule with direct motion. There's vibrational, where atoms in a molecule, they sort of move toward one another, like over and over again. So you can think of them like springs. So they're separating, but the bond that holds them together is bringing them back. Separating, bringing back. And then there's finally rotational. So if we think of a molecule of water, it's going to have an axis around right here, and it's going to be rotating around this axis. That's what rotational that's what a rotational microstate would look like. So that's just a reference to sort of understand what's going on, but all in all of these movements are happening inside of a substance, right? So what this tells us right here is that our change in entropy is going to be greater than 0 when we transition from these states, these macro states, from a solid to a liquid or from a liquid to a gas. We know that we're going to have a positive entropy. And we know that we're going to have a negative entropy if we're transforming into something more orderly. So from a gas to a liquid, or from a liquid to a solid. Or it could also be from a gas to a solid, or similarly to how a solid can transform into a gas. So alternatively, there's also another definition that we can dictate the sign of our change in entropy. So when the number of molecules increase, we're going to have a positive change in entropy. And think about it this way. If you're getting more and more molecules inside of a macro state, what's going to happen? Well, it's going to become more unpredictable, and therefore, there's going to be a lot more microstates to calculate. So therefore, by this equation right here, the more microstates we have, the more our entropy increases. So we can say that entropy is proportional to our quantity of microstates. More specifically, our entropy is proportional to the natural log of our microstates. And here I have a formula that we can sort of grasp. So we have 2 moles of ammonia, and that's going to decompose into 1 mole of nitrogen gas and 1 mole of and 1 mole of hydrogen gas. So all in all, this is 2 moles of ammonia, this is 2 moles of nitrogen total, and this is 2 moles of hydrogen total. So this is equivalent to 4 moles of individual atoms and individual atoms, right? Like making up these bonds. That's what I mean. So here we have 2, and then we go from 2 to 4. So therefore our entropy increases. And it's going to decrease if we have the reverse. So we have nitrogen gas and hydrogen gas bond to make 2 moles of ammonia gas. Because this right here is 2, and this right here, as we mentioned, is 4. Okay, so now we have these 4 general ideas that we can keep in mind for standard entropies. Like, we have our standard enthalpies, right, which is delta H with a little degree sign. And we know that at 25 degrees Celsius, for any compound in its standard state, or like an element of some sort or the like, it's going to be equal to 0, right? Well, for entropies, it's going to be quite different, because the standard molar entropies at 298 Kelvin, they are not equal to 0. So this is where you usually have an appendix C or some kind, and you have a reference to what the entropies are going to be. Maybe a table is given to you, and that's something we'll get into. Also, the standard molar entropies of gases are going to be greater than the standard molar entropies for liquids and solids. And that is simply something that we reviewed over here. A gas is one that you can say maximizes entropy of a substance, and the solid is a minimum of entropy. Obviously, we're not talking about other kinds of macro states like plasma and all that like, but for these 3, that's all we're gonna worry about. And also, standard molar entropies increase linearly with moles of substance. So that's something that was defined by this equation, the 3rd law of thermodynamics. And that's something we see here, right? Also, our standard entropy increases with increasing number of atoms in formula of substance. So again, it's pretty self-explanatory. We get that the more moles that we have, or the more number of atoms that we have, we're going to have many more microstates. Okay, so now we can get into our practice problem. And this is one that I got from my textbook. And it says, calculate the change in standard entropy for the reaction at 298 degree Kelvin. So it gives us aluminum oxide plus 3 moles of hydrogen gas is gonna give us 2 moles of aluminum, still a solid, and 3 moles of water vapor. So what we have to do for this is we have to look up our standard entropies. And the way that we're going to calculate this is going to be pretty simple. It's going to be the same way that we calculate our delta H. And it's going to look something like this. It's going to be equal to our products minus our reactants. And you'll see what I mean. So the entropy for aluminum oxide, I'll look it up right here, is going to be 51.00 joules per mole Kelvin. For our hydrogen gas, let's see, it's going to be 130.58 joules per mole Kelvin. And that will give us, obviously we're looking also at their states, don't forget to check those. That's going to give us 2 aluminum as a solid, that is 28.32 joules per mole Kelvin. And next we have water vapor. So for water vapor, if we look at the state, again, it's not a gas, but it's not a liquid, it's a gas. So it's going to be 188.83 joules per mole Kelvin. So now, what we need to do is we need to look at our molar ratios. So here we have 1 mole of aluminum oxide. Here we have 3 moles of hydrogen gas. Here we have 2 moles of aluminum, and we have 3 moles of water vapor. So now, what we're gonna get for our new values is we're gonna get 51 for this one, joules per Kelvin. Remember to take out the moles. Next we have 130.58 times 3. So we have 391.74 joules per mole Kelvin. Next we have 28.32 times 2. So that'll be, I said don't forget to take out the moles, and then I placed the moles. How curious. And next we have 56.64 joules per Kelvin. And finally, we're gonna have 566.49 joules per Kelvin. So now, what we're gonna do is we're gonna flip these. We're gonna flip these quantities. So we're gonna add these two. We're gonna add these two, and we're gonna get the difference from these. So what I'm saying is we'll have this quantity on the left side, right? It'll be our products minus our reactants. So it'll be 566.49 plus 56.64. That gives us 623.13 joules per Kelvin minus our reactants, which is 51 plus 391.74, and that gives us 442.74 joules per Kelvin. So therefore, our change of standard enthalpies in this reaction is going to be 180.39 joules per Kelvin. And remember, this value is just the one that we calculated here, and this value is one that we calculated right here. So you can think of these as your products of standard enthalpy minus your reactants in terms of standard enthalpy. So that is how to solve these kinds of problems. So that'll be all for this video. I hope you find this helpful. If you have any practice problems or any questions, you can let me know, and I'll do my the best in my ability to answer them. Thank you for watching.